In this video, what we're going to do is talk a little bit about the foundational principles that govern a lot of physics. And in particular, what we're going to do is talk about these things that we call conservation theorems. You've already seen these before in mechanics. And so let's put a few of them up there. So first, if you're thinking about a system, its change in momentum is equal to the external force that is applied to that system times whatever the time change is. If you look at the energy change of that system, that's equal to whatever the external work is, plus whatever thermal exchanges you have. And if you look at the angular momentum of that system, that's equal to the torques that are exerted on the system times the amount of time over which the torque is applied. Now, we referred to these as fundamental principles in mechanics. They help us predict a lot about what's going on with the system. But they're also often described as conservation theorems. And the reason for that is because they tell us when quantities of the system don't change, right? So when does the momentum of the system not change? Well, the momentum of the system is conserved when there's no external force. The energy of the system does not change when the external work plus any thermal exchanges vanish. There's angular momentum conservation when there's no external torques. This is all stuff that we learned in mechanics. But now, because matter is charged, we actually have a new fundamental principle, a new conservation theorem, namely that the charge that is associated with the system will increase or decrease when there is external current that crosses the boundary. So this gives us a conservation theorem, namely that the total charge associated with any system will not change when there's no external currents. So this is our new conservation theorem that tells us about electricity and magnetism. And in fact, all of these conservation theorems still apply in electricity and magnetism. It might not be obvious why they do, because it's somewhat complicated. So let's take an example. The linear momentum conservation theorem applies in electromagnetism because electromagnetic radiation, right, electricity and electric and magnetic fields taken together can actually exert pressure on material. This happens in stars. So when you have this fusion happening and you have electromagnetic radiation waves sort of getting pushed outward from the core of a star, it carries with it linear momentum that can push on the gas that's in front of it. Now, without that push on that gas, the star would collapse under its own gravity because it has material outside that's attracted to itself. And so that electromagnetic radiation, that radiation pressure, that momentum that's carried by the electromagnetic radiation keeps the star in the shape and size that it is. And in fact, when a star burns out, it can burn out in a way where that radiation pressure drops off, the star collapses, and then explodes. That's a core collapse supernova. So that is a very clear example of the electromagnetic radiation carrying momentum. That is a complicated affair. It is something that we will not cover in an introductory course, but it is something that's important. In addition, electromagnetic radiation can carry angular momentum as well. It can actually act to turn things, but we won't get into that either. The ones that you're probably most familiar with, though, is energy conservation and charge conservation, because both of those actually show up when we talk about circuits. Those are easier to see than the other two because they're ones that are very easily exemplified in a circuit diagram. So let's take a circuit that just has a resistor like this. And what we can do is we can apply this idea of energy conservation to the circuit first. So the battery that is connected to this circuit is a source of energy. It provides an electric field that will drive a current around the circuit. And so this guy is a source of energy that allows us to drive this current. All of the other parts of the circuit are users. So in particular, the resistor is a user. And the way that we talked about this in thinking about circuits was we thought about, instead of the total energy of the circuit, we thought about the electric potential energy per unit charge. So how much energy does it cost for every little charge that I move around the circuit? So this is the total potential energy divided by the amount of charge. And what we found was that the amount of electric potential energy per unit charge provided by the battery was exactly the amount that was used in a resistor, barring the wires being having some resistance, right? And so the idea there is that if we look at the amount of energy provided per unit charge by the battery, exactly that amount is being used by the resistor. So if we take the whole circuit to be a system, the total amount of energy per unit charge is conserved. Exactly how much energy per unit charge is provided by the battery is used to drive all of the charge through the circuit. Now, one of the other principles that came into play was how charge conservation works. So let's rewrite that guy. So what we're saying is that when we look at the circuit, there's only a given amount of charge. That makes sense because if we consider the circuit to be a whole system, there's not any charge crossing this boundary, like coming onto the circuit. It's all contained within the battery and the wires and the resistor and so forth. That's not super helpful, right? The fact that that total system has some conserved amount of charge. What's helpful, though, is that on the other side of this, that suggests that the total external currents vanish. That means if we take little parts of the circuit and we look at what's going on in little parts of it, the amount of current that's going in through one part of the circuit has to be the same amount that's going out. Because otherwise, charge would build up in the circuit. So what we can do is we can take a little piece of the circuit. We can say, well, I want to look at it here and here, right? So the current is going to go around this way. It's going to come out that way. And if we look at these two parts, what this tells us is that there's no buildup of charge anywhere in this part of the system. And therefore, the amount of current that I see going in here is exactly the amount that's going out. Now, this result is our steady state assumption for circuits. That steady state assumption tells us that the total current in any branch of the circuit is going to be the same. If we have a more complicated situation, so for example, if we have a situation where a circuit branches off into two parts, for example, like this, which is something that you've analyzed before, we can take that whole thing in the steady state, and we find that in the steady state, the change in charge is going to be equal to 0. Therefore, there's no external currents. Therefore, the current that goes into this location here is exactly the amount that comes out of both sides, right? So that would say that I in is equal to I out 1 plus I out 2. Use this quite a bit to analyze circuit diagrams, right? To be able to say something about what's going on with the current through different parts of your circuit. And you use this as well. So what we've done here is we've actually talked about general conservation theorems, right? How all of those fit together, how they all work with electricity and magnetism, and specifically how the ones that we use most often, at least in the introductory courses, have to do with energy conservation, namely that the amount of energy per unit charge available in a circuit gets used up by going through the entire circuit, and that charge conservation tells us precisely how the currents are going to add at any specific branching point, as any specific node where the circuit breaks up.